Hi, my name is Manish Gupta, and in this video, I'm going to talk about our recent work on DQAC, which is about detoxifying query auto-completion using adapters. This work is in collaboration with folks from IIT Hyderabad, specifically Aishwarya Kaushal and Professor Bonendra Shankar Desarkar. Right? This work is also going to be presented at PAKDD in May 2024. So let's get started. So why is toxicity, a problem in query auto-completion? So for query auto-completion, essentially we use natural language generation models so as to increase the recall in cases where our try data structure does not contain enough completions for a user prefix. Now, natural language generation models, as you know, can generate harmful, offensive, or inappropriate suggestions. This basically leads to toxicity in query auto-completion world that needs to be tackled. Now, detoxifying query auto-completion problem can actually be modeled as a controlled text generation problem. You can think about it as a controlled text generation problem, where the input is the session of queries that the user has fired so far, prefix, the current prefix, the partial query that the user is trying to type, and then a complete query. So the input is a session, a prefix, and a complete query that the user will type. And of course, this input is basically used at train time. At test time, of course, you don't have the complete query, and you have to essentially guess a non-toxic complete query. That's the goal, right? The goal is to generate 10 completions such that they are as close to actual human queries, human-generated queries. They are relevant with respect to session. They must be, of course, relevant to what the user has been doing so far, and they must be non-toxic. Okay, that's the goal. Now, typically, the way people have tried to mitigate toxicity in query auto-completion world is by using block lists of toxic words. So, but the problem with any kind of list-based mechanism is that the list need to be constantly updated. There could also be some, false positives. So, for example, of course, this particular query is sort of toxic, but actually this is a popular song, and therefore, even if it contains a toxic keyword here, you cannot really mark it as toxic and just not show that particular song in your dropdown. Okay, so. You could also detoxify text generated by, the pre-trained language models using controlled text generation where the controlled text generation is achieved through fine tuning by using clean data. But then the problem is where to get this clean data from, right? Especially in the query auto-completion world, given a large bunch of query logs, how do you figure out which ones are clean anyway, right? There are also methods which have decoding, they're called as decoding time algorithms for controlled text generation. You don't really train a specific model for non-toxicity, but then at decoding time, you try to avoid generation of toxic things. But then when you're trying to do decoding time kind of changes, it basically increases latency. And remember, in query auto-completion world, you have to actually compete with users typing speed. So increasing latency is not really acceptable. Lastly, there are also reinforcement learning techniques to unlearn the toxic content. And as I'll talk about in this video, you will see that they are not as accurate as the one that we propose in this work. So now let's basically, as to be able to actually detoxify things, we need to actually have a measurement of how much toxic a particular query is, or a particular query completion is. Right. So therefore, what we need is a toxicity classifier for search queries. Now, there exist some models which basically can evaluate, given a piece of text, whether it is toxic or not. However, these models are not trained on query auto-suggest datasets like Perspective API, Detoxify, and Toxigen. Right. The other thing is, as the name itself says, it's an API. So what we need is an offline tool so as to evaluate the toxicity of search queries. Okay. And therefore, what we do is to first build QDETOXIFY, query detoxification kind of tool, which tries to evaluate what is the toxicity score for a particular query. So we, in fact, initialize this model using Detoxify itself, Detoxify being a popular detoxification or a toxicity classification model, right? Which is based by itself Roberta fine-tuned with Jigsaw dataset. Yeah. We train it with the labeled query log from Bing. So at Bing, we have lots of labeled query log, whether a query is toxic or not. We basically train this model, Detoxify, fine-tune it using this Bing query log data. And essentially, we use about 8 million training instances. and 100K validation and test examples so as to basically build this QDETOXIFY model and also evaluate its performance. So QDETOXIFY on this particular test set essentially gives us 95.96, almost 96% accuracy, while Detoxify itself, the publicly available model, gives us 82.82% accuracy. So this basically says, brings out the need why we actually needed a specific toxicity classifier for query logs, right? However, if you look at it, the correlation between their outputs is about 0.8, which basically says it's more or less doing similar things as Detoxify. Now, as an example, this particular query with all those dots basically is rated as toxic by Detoxify, but QDETOXIFY nicely rates it as not toxic. Okay. So now that we have a toxicity classifier, let's look at our generation model, which basically generates non-toxic stuff. Okay. So we basically depend on GPT-2 as our base model. Therefore, our model is a transformer decoder model, and therefore it can be used for generation purpose. We start with a pre-trained GPT-2 model, and then fine-tune the base pre-trained GPT-2 model using a large personalized query auto-suggest dataset. So by personalized, we just mean that it can actually take session information also as input besides taking only the current query. Okay. So we fine-tune this model using a large personalized query auto-suggestion dataset, and we'll call this model as personalized GPT-2. Okay. Now you take this personalized GPT-2 and then so this is a standard transformer layer. As you see, of course, it has the multi-head self-attention, and it has also this feed-forward neural network, feed-forward the FFN sublayer in the transformer decoder layer, right? And in the transformer GPT-2 layer, right? And what we do is to basically transform this as follows. So you actually have the multi-head self-attention. You also have the feed forward, but then on top you actually have two adapter modules. These are small little layers, so which basically take your feed forward layers output and then perform layer normalization and of course all of those things. But then mainly they perform the down projection to a small bottleneck size, and then an up projection so as to essentially get the overall output. So each of these A plus and A minus, A plus is basically called as the non-toxic adapter, and the A minus is called as the toxic adapter. Okay, so we basically use the concept of adapters, which basically help you adapt the generation to a certain style. Okay, so the toxic adapter will be basically trying to push the generation towards a toxic style, the non-toxic one towards a non-toxic style in that senses. Okay. So that's that. So we train it one by one. So we train the toxic and the non-toxic adapters one by one. And then at inference time, essentially the way we use them is that we actually have the multi-head self-attention, the feed-forward network, and also the toxic, non-toxic, and the base generation. All three of them are combined with some parameters. So we basically have some parameters alpha here, so as to combine the overall generation, and that gives us the final output. Yeah. So the way the final output is obtained, you basically start with HI, which is basically the input to this particular layer from the previous layer. You perform layer. Sorry, the HI is basically right here. So after you have done all the feed forward and the multi-head self-attention and so on, you take the HI, do layer normalization, apply a down transform, apply this down projection layer, do a ReLU up projection that gives you the adapter output. Now, depending on the parameters that you use, you can basically get the adapter output, from the positive adapter and negative adapter. And then your overall output is going to be the original HI, along with the Ri minus and Ri plus coming from the two adapters, Ri minus and Ri plus coming from the two adapters with a weighing factor alpha. Okay? Alpha sort of controls the amount of steering over the base language model that you want to bring in. Okay. So now the DQAC model training sort of involves three steps. How do we train this architecture, right? So I talked about the architecture in the previous. How do we train this architecture? Well, we incorporate the personalized context by fine-tuning GPT-2 small to get personalized GPT-2, as I mentioned on the previous slide, right? So you get the personalization effect in the GPT-2 model, and plus you basically make the model understand how to generate, make the model understand the auto-completion task, basically, right? Query auto-completion task. The second step, you basically train the toxic adapter. And while doing this, you freeze the rest of the model parameters, including the non-toxic adapter parameters also, using a human annotated toxic QAC dataset. So now here you need a human annotated toxic query auto-completion dataset. You need basically queries which are toxic in nature, right? And third step, basically, you train the non-toxic adapter while freezing the rest of the model parameters, including the toxic adapter that you just trained. Okay, so that's that. Overall, the training essentially uses the auto-completion loss. So, of course, cross-entropy loss computed over auto-completions. So, essentially, here S is a sample from this adapter dataset. So, essentially, it could be a negative adapter dataset or a positive adapter dataset. And you want to maximize the probability of seeing the actual query completion that was present in the dataset, given the session, given the current prefix, and given the initial adapter parameters. Okay. So that's that. Now, as compared to the most popular, another popular model, DXpert. So if you know about DXpert, DXpert is another popular model for non-toxic generation. Okay. However, DXpert actually is a combination. It's sort of an ensemble of three different models: base model, expert model, and a anti-expert model. So they train actually three different models, rather than us, where we basically train only one base model but train two other adapters. So our adapters are much smaller in size. DXperts, in fact, requires 3 times more RAM compared to our model because our adapters are so small, they're hardly contributing to the overall size of the model. DQAC also has no additional latency overhead. So since DXperts has three different models, you have additional latency that you require in terms of doing inference over three different models. DQAC also operates in the latent representation space rather than in the output space. So the way DXperts actually generates the output is that it passes the input to each of these three different models, and then finally at decoding time at the output layer, it basically does a combination or an ensemble of the outputs coming from these three models. While we basically do these combinations in the adapter layers in every transformer layer, so basically thereby improving the effects of this toxicity and non-toxicity appropriately in the entire model reasoning rather than only done post hoc or ad hoc at the end. Okay, so we experiment with two different data sets, Bing and AOL query logs. We also have data sets, for personalized QAC training, personalized query auto-completion training for both Bing and AOL query log. Right. But adapter data we basically have only for Bing, which is a small toxic and non-toxic labeled data set, about 40K each. So remember, all of these data sets are disjoint from each other. So PQAC data is actually different from adapter data. Okay. PQAC data could have some toxicity by itself in it, but we've tried to keep it as clean as possible using our QDETOXIFY model. Right? Train validation test splits are done in a temporal way so that the test splits are more recent queries. Okay. The split, so essentially to identify personalized sessions, we typically follow the standard definition of a session, where the idea is basically within a session, two queries should be less than 30 minutes apart from each other, and of course coming from the same user. Okay. Yeah, so now to get the query auto-completion part, you have to take a query and get the prefix and the suffix part, right? So in AOL dataset, unfortunately, we do not have the prefix and suffix separately. So we basically synthesized prefixes by randomly splitting a full query at any point in between, at any character in between. For Bing, we actually have the real prefixes typed by users, so from Bing query logs, and therefore we leverage them. For Bing, the PQAC data, this personalized query auto-completion data consists of 20 million for training, 101K for validation. For AOL, it consists of 4 million. For AOL, the overall data consists of 4 million for training, 100K for validation. Okay. Our evaluation is basically done on two kinds of data sets. So where the query auto-completion could be non-toxic or toxic. So of course, users type toxic queries also. So for our evaluation, basically try to take toxic queries also, and where the prefix is non-toxic in nature, and try to see if our model can actually generate the non-toxic completion rather than being being very aligned and generating toxic query auto-completion. So in case of NPTQ, we do not really care about fidelity with respect to generating the exact query that the user typed, because the user actually typed toxic queries, right? But in the NPNQ test set, we basically want to ensure that our model is also capable of generating high fidelity queries, exactly what the user wanted, in case the user actually typed, in case the user intent is a non-toxic user intent. Okay. So that's that. Now, there are these details about their test set sizes, but that's not very important. You can look at them in the paper also. So to compare, we looked at several baselines. So a personalized GPT-2 itself, which basically is not toxicity or non-toxicity aware, it's just a personalized GPT-2 model. We also looked at domain adaptive pre-training in the sense that we took a personalized GPT-2 and continue to fine-tune it with the 4 million non-toxic queries. Okay, and we hope that since it has been fine-tuned on non-toxic query, that should basically generate non-toxic stuff, right? We also experiment with compare with PLM, DXperts, Quark. All of these are popular models for non-toxic generation. Lastly, we experiment with our own baseline ablations. So just the toxic adapter or just the non-toxic adapter, which enable only one adapter. So either the toxic adapter or the non-toxic adapter. Okay. Um, that's that. Now, of course, notice that our model consists of these three things. So essentially, we have the generation done by the base model, the generation done by the toxic adapter, and the non-toxic adapter. And clearly, our overall combination ensures that we not just have the base generation, but we want to ensure that our generation is steered towards non-toxicity and away from non-toxicity by having that minus sign. Right? So that's that. So we measure our performance in terms of standard metrics for retrieval as well as in terms of toxicity, right? So to ensure that we generate completions as close to the actual human completions, we measure it using the standard MRR metric, the mean reciprocal rank, and also semantic BERT MRR. So MRR basically just cares for the text-based, the syntactic match, while semantic match-based MRR actually cares for whether the intent is preserved or not. So semantic BERT, using semantic BERT embeddings. Okay. Of course, we also use Blue and Blue RR, which basically are measures for figuring out generation quality, standard measures for figuring out generation quality as such, right? For toxicity purpose, we actually measure average max toxicity. So, which is basically average of the maximum toxicity over 10 generations for a test example. Remember, in auto-completion, you need to show a drop-down. So we generate 10 things from a generative model. And the average maximum toxicity, average of the maximum toxicity is basically average max toxicity. Okay. So you take the max toxicity over that block of 10 generations, and then you average it out over the entire test set. That's basically average max toxicity. Empirical toxicity probability, so the probability of at least one of any 10 generations being toxic is basically what is basically the empirical toxicity probability. And of course, we average it over the entire test set. So here are the overall results. We show results over the Bing dataset and also over the AWorld dataset. Okay, the alpha we used was 2.6. Remember the parameter, hyperparameter, which sort of controls how much you want to care for toxicity and non-toxicity versus the usual generation. In the adapters, we use dimensionality of d equal to 8. Basically, that's a very small bottleneck dimension, making sure our adapters are very small in size. We use a beam size of 10, get 10 generations, because in the dropdown, we want to show 10 things, right? Max generation length is fixed to 80 characters, 80 tokens, right? Now, so let's look at the results. We compare against several baselines, and we also compare against two of our own, our own ablation methods, and DQAC is our full method. Now, the comparison is done over, let's look at the lower one first. Comparison is done over MRR, SBMRR, which are and RR blue and blue. Those are quality metrics from a generation perspective. Also, you see that this reports results over the union of the two data sets, the toxic and non-toxic data sets, test sets, basically, right? And then from a toxicity perspective, we report the average max toxicity and the probability of toxic generations using both QDETOXIFY and Detoxify. Okay. So what do we observe here? So we observe that in the AWorld dataset, at least, if I look at personalized GPT-2, that generates high fidelity generation. So basically, it matches with the user's query intent much more. If you look at DQAC, however, it basically generates things with the lowest toxicity. Right, so that's the nice part. So if you look at the DQAC, generations, well, they are basically on the MRR side, they're actually lower MRR. Okay. Now you might be thinking, oh, low MRR is bad, so that's not good. But then the interesting point is, when you're doing detoxification, of course, you do not want to generate toxic stuff, which basically means that you are not going to match with the ground truth tokens if the ground truth tokens were actually toxic in nature, which basically would mean that you will get a lower MRR anyway. And I'll give you examples later to basically show how this also leads to lower semantic semantic BERT MRR, because yes, you don't want to follow the same toxic intent anyway. Okay. Now, for Bing, we observe similar results. For Bing, of course, fortunately, or rather, for Bing, essentially, we cannot report the actual results because of confidentiality reasons. And therefore, what we've reported is delta results with respect to the personalized GPT-2 model. Okay. So everywhere, so whether it is the quality of the generations or it is the toxicity, we have always reported the delta results. Okay. So what you observe is that our toxic and our non-toxic adapter basically reaches 95% in terms of MRR with respect to personalized GPT-2. So actually on Bing dataset, we are actually doing very good, right? So from a MRR or a SBMRR quality perspective, we're actually doing pretty good, blue and blue RR perspective as well. Okay. However, what is interesting to note is that on a toxicity perspective, we are doing awesome. Right? So compared to other models like PPLM, which actually has like 40% more toxicity and other things, we basically have just 30% toxicity of the personalized GPT-2 model, right? From AMAXT perspective and so on. So the toxicity in our model actually is much lower compared to the toxicity in other models, while the generation quality is near okay. It's basically reasonably good. Now, also the generation quality, if you notice in the AOL dataset is lower because remember in the AOL dataset, we do not have adapter data, which basically would have caused slight degradation with respect to the kind of tokens that are generated in older world compared to newer world. So if you know, AOL dataset is from very, very long, it's a historical dataset. It's probably somewhere around 2007 time period. So therefore, the tokens are actually of historical queries rather than very recent queries, while the Bing data is actually very fresh. So the train and test is both done on the fresh data, while in AOL case, the train is basically done using, train the basic model using Bing data, but the adapters using again Bing data, but you test on AOL data, which is basically older historical queries. Okay. Now, if I basically look at NP-TQ and NP-NQ, those two subsets separately, what I observe is that in NPTQ, remember these are toxic queries. So T stands for toxic, so they're toxic queries, while these are non-toxic queries, non-toxic queries. Okay. So if you notice in non-toxic query case, our quality values are also pretty good, right? While in case of a generation of toxicity, of course, we basically this is non-toxic queries, right? So essentially, there's not much toxicity in them anyway. So in terms of toxicity, we do not really change too much of stuff. But in case of toxic queries, we change a lot of stuff, basically meaning our quality is okayish. I mean, if you compare with other non-toxic generation models, we basically retain a whole bunch of quality in the queries. The intent in the queries, try to retain as much intent in the queries. However, if you basically look at the overall generation toxicity, our toxicity is much lower. Our toxicity is way lower. Okay. So here is an analysis why toxicity reduction basically means that your MRR will reduce. Okay, so look at this example. Let's say the prefix is the user type piece of A. Right? Now the ground truth is of course a toxic keyword completion, but DQAC generates piece of analysis. Now clearly intent-wise, or even if you compare in terms of tokens, your token is very different, right? So your MRR is going to be low, but your toxicity score has been reduced significantly, right? So you're basically showing a non-toxic completion. Similarly, look at this another example. The session in this session, basically the user has been typing things like braces and not so good queries, right? So basically the user has been typing a lot of adult queries out there, right? And then of course the user types teen. Now the reference completion is teen, braces, and then toxic keywords and so on. If you look at several of these baseline models, they also generate toxic generations. Okay, of course, I've hidden the toxic keywords, but you can actually look at them in the paper where we have shown those toxic keywords also. Okay, but if you look at DQAC, it basically generates very nice completions: teen braces white, YouTube, teen braces YouTube app, and teen browse Facebook, and so on. Okay. So when we did human evaluation, we found to basically quantify semantic difference and contextual alignment, we found that about 94% of the examples display semantic differences from the reference. And that's basically going to happen because you don't want that toxic intent to be captured in the completions that we are coming up with. While 84% of the examples maintained contextual alignment with the prefix and the session. So of course, lexical alignment with the current query was not there, but if you care about the session, it basically sort of tried to align in a large manner, largely in that ballpark. Okay. So overall, to conclude, DQAC generations are non-toxic and semantically different from the ground truth. In summary, in this video, I talked about DQAC, which is a detoxifying model for query auto-completion systems, which tries to mitigate toxicity in query auto-completion. It is based on controlled text generation with adapters. The QDETOXIFY model, essentially, we also contributed a QDETOXIFY classifier model, which is basically query toxicity evaluation model. And lastly, we did comprehensive evaluation using two real-world large-scale data sets from Bing and from AOL. That's it. Hope you like this video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.